are given that the group G is abelian and we are considering the subset H of G. H is defined as set of all x in G such that the order of x is finite. Now we have to show that H is a subgroup of G. So if we are showing this, then we will essentially show that the set of all elements in a abelian group with finite order, that collection will be a subgroup of G. Okay, here G could be finite, infinite, anything. If G is abelian, then the set of all elements in G with finite order will form a subgroup. That is the crux. Okay, so let's proceed to prove this. So we can either use the one-step subgroup test, or we can just go by the definitions. Here, let's go by the definition. Okay, so to show that H is a subgroup, we must show that H is closed under the operation. That is, we have to show given any A and B in H, we have to show that AB is in H. Okay, now, the associativity of the operation comes for free, right? Because the operation is defined on G and G is a group, so the operation is already associative. So, since we are just restricting the operation onto H, it does not matter. It will still be associative. Okay, associativity comes for free. We need not check it. Next, we have to show that the identity element is there in the subset, and then we also have to show that given any element in H, its inverse is also there in H. We have to show these. Okay, so these are the things that we are asked to show. Okay, so let's go here. Definitely, see here we have that uh, identity element e raised to 1 is actually E, right? And we know that order of E, we can either denote it by this or we can write it as O of E. Okay, so order of this one is 1, which is finite, which is less than infinity, that is finite, right? So definitely identity element is there in H, correct? So our second condition is definitely satisfied. Okay, now uh, okay, the first one, let's begin with the first one. Okay, so let a comma b be in H. Okay, then we know that order of A is finite. Let's call it some m. Okay, now order of B, it can be some n. Okay, both m and n are finite. Okay, now we have to show that AB is also there in H. What is the condition that AB must satisfy? To be in H, we must show that order of AB is finite. Okay, so what do we observe? First, we observe that AB whole power this m into n. Just consider this. Okay, this is actually equal to AB into etc. like that AB mn times, right? Now, since it is abelian, we can actually bring all the a's together and we can bring all the b's together. So we will have a power mn into b power mn. Okay. Now, using the properties of exponents, we can write this as a power m the whole power n into b power n the whole power m, right? Because it is mn, so I can split it like this. So we have a power m whole power n into b power n the whole power m. Okay. Now, what is a power m? We know that since order of a is m, we have that this is actually equal to identity, and it will have identity power n, which is operated with b power n is again identity power m, which is identity. Okay. So what did we show here? We showed that ab whole power mn is identity. Okay, so we have that ab power some finite number is definitely identity. So we'll have that order of ab is less than or equal to mn. See, note here, we have not said that mn is the order. Okay, to be the order, mn must be the least positive integer such that ab power mn is identity. Here we don't know if mn is the least or not. Okay, We just know that AB power mn will definitely be identity. That much we know. But if it is least or not, we don't know, right? So we cannot conclude that the order of AB is mn. But definitely we know that if AB power mn is definitely identity, then it the the order of AB, the least positive integer such that AB is identity, must be less than or equal to mn, right? Mn is a large number and AB power mn is definitely identity. So its order, the least positive integer, say for example k, such that AB power k is identity. Okay, that k will be the order, and that must be less than or equal to mn, right? Mn is a positive integer, and it is a big number. Now its order, that we know at least AB power mn is identity, so the order cannot exceed mn. Okay, and the order may be less than also, so order of AB is less than or equal to mn, right? Now in fact, we know more, but at this stage, I'm not saying this. It will be a divisor of Mn and things like that. But anyway, order of AB is finite, right? Because Mn is finite. So order of AB is finite. Okay. So AB is in H. So the first thing we have already taken care of, right? Now the next thing we have to show the inverse, right? Now we have to show, that's what we have to show. To show A inverse is also in H. Okay. Now, that is to show order of A inverse is finite. Correct. So, now let A be in H. So, since A is in H, we know that order of A is finite. Call it M. Okay. Then we have that A power M is identity. Correct. Now we will multiply on both sides by a power minus m. Or okay, let's do it some other way. Now consider A inverse the whole power m. Okay, consider A inverse the whole power m. Now what will we have? We will have that A inverse the whole power m into A power m. Hmm? This will be equal to, here from the left, here what are we doing? We are multiplying by A inverse the whole power m on both sides, right? So we'll have A inverse the whole power m to identity, correct? Now here the A inverse the whole power m, we know this is abelian, G is abelian, and we will have that AB the whole power m will be equal to A power m into B power m, definitely. Okay, so here we will have that this is actually equal to A inverse into A the whole power m. Okay, this is actually equal to A inverse the whole power m, right? Because multiplying by identity does not create a difference. So here A inverse into A will be identity power m, which is nothing but identity, will be equal to A inverse whole power m. So again, what did we get? Here we got that um, A inverse when raised to m will definitely give the identity, right? So again, order of A inverse must be less than or equal to m. Okay. Again, what did we have here? M is a positive integer such that A inverse the whole power m is identity. But we don't know if m is the least or not. So at present, we can only say that order of A inverse is less than or equal to m. And that's all we want, right? Because m is finite. So order of A inverse is finite. This m is finite. Okay. So order of A inverse is finite. Because it is less, order of A inverse is less than or equal to m. M is finite, so order of A inverse is also finite. That is, A inverse will belong to H. So whenever A is in H, A inverse is also there in H. So given any A in H, A inverse must also be in H. Correct? So we have proved the third one as well. So the subset H satisfies all these three conditions, hence H is a subgroup of G. Okay, so essentially what have we proved? Here we have proved that in a abelian group, set of all elements with finite order forms a subgroup. All right.